Hello, good evening friends. In today's class, we will solve some numericals on steam nozzles. Okay, so to solve some numericals on the steam nozzles, we required some basic formulas, some equations. So first, we will list the required equations, the required formulas used for solving numericals on steam nozzles. The first one, the basic formula is mass flow rate of steam which is flowing through the nozzle will be calculated using the continuity equation rho AV, where rho indicates the density of steam, kg per meter cube, A is the area of the nozzle, V is velocity. As I told you in the previous video lectures, so velocity can be represented with V, or some textbooks they will note down with C. Okay, so you can use C or V. So I have done both here. And reciprocal of density is specific volume. So 1 by specific volume is density. So A into C divided by specific volume. So this is the one basic formula will be used for solving mass flow rate of steam. The second formula is discharge. So Q is equal to area into velocity. So unit will be meter cube per second. And the third one important formula which will be used many times for solving numericals. And P2 by P1, that is called critical pressure ratio, is equal to 2 divided by n plus 1 into n by n minus 1. Okay, so these are the most important equation which we use for solving the numericals. Okay, so where and dear students, remember, so P2 is pressure at throat if it is conversion diversion nozzle. Otherwise, if it is a conversion nozzle or if it is diversion nozzle, P2 indicates exit pressure at the nozzle and P1 indicates inlet pressure at the nozzle, as N represent index of expansion. And we need to remember the three values of N. One is, if the value of N is 1.035, that is for wet steam. In the numericals definition of problem, he will give the quality or the condition of steam at inlet to the nozzle, whether it is wet steam is flowing through nozzle or dry steam or superheated steam. So based on the quality and condition of the steam, you have to choose the value of N. So this value will be given in the problem or will not be. So you have to remember. So do remember this value of N. And the last one more formula for calculating velocity at exit of the nozzle. We derived one equation, one derivation for this. So usually V2 or C2 is velocity, that is a square root of 2000 into K. K is a friction factor. So in the numericals he may give or may not be given. So if given, consider the value of K, that is friction factor, or else you neglect it. And into difference in enthalpies, that is H1 minus H2. H1 is enthalpy at inlet of the nozzle and H2 is enthalpy at outlet of the nozzle, plus C1 square, that is velocity at inlet of the nozzle. 90% the value of C1, that is velocity at inlet, will be neglected, but if it is given in the problem, you consider the value of C1 and calculate C2. Okay. If you neglect the value of C1, the above equation V2 will be written as square root of 2000 H1 minus H2 into K. So most of the times the K will not be given, you can neglect it. So square root of 2000, if you make it in the calculator, you will get 44.72. You can use this equation or this equation. Now the condition velocity for superheated expansion, that is metastable condition. So square root of 2 into n by n minus 1, P1 specific volume into 1 minus P2 by P1, n minus 1 by n. These are some 4 to 5 formulas we have listed here. Now we'll take one numerical which is asked in the previous question paper, Visvesvaraya Technical University, July 2019. The subject code is 17ME43, question number 10B. Okay, here we will read the problem now. The steam expands from 3 bar to 1 bar, means initial pressure and final pressure is given in a nozzle, and here he has not mentioned particularly what type of nozzle it is, convergent or divergent or convergent divergent nozzle. Okay, so we will decide later. The initial velocity is 90 meter per second. So 90% this velocity will not be given, but in this numerical he has given. So you have to consider initial velocity in the formula and calculate the required unknown. And initial temperature 150 degrees Celsius. So determine the exit velocity of steam following two cases. One is expansion is isentropic in the nozzle. So what he has asked, determine exit velocity assuming that the flow is 100% ideal, that is isentropic case. And second unknown, determine the exit velocity but the nozzle efficiency is 95%. So remaining 5% is error. So it is irreversibility. It is non-isentropic process. So it is non-isentropic process or irreversible process. So for these two cases, we have to find the value of exit velocity. And dear friends, there are two methods to solve numericals on steam nozzles. One using steam tables, or we can use a Mollier chart. Okay, so first using steam tables we will solve this numerical. Then the same numerical will solve again with the Mollier chart, and we will compare answers of both. The answers of using steam tables does not match exactly with Mollier chart. There will be a slight difference between the answers. Okay, so first we will go to method 1 using steam tables. So first we will write the given data. Whatever the data is given in the numerical. The steam expands from 3 bar, that is inlet pressure, that is I will take it as P1, 3 bar, to 1 bar. So final pressure is 1 bar, that is P2. In a nozzle, the initial velocity is 90 meter per second. Here initial velocity will be represented by V1 or C1, so 90 meter per second. Initial temperature is 150 degree Celsius. So pressure at inlet, temperature at inlet, both are given. So we have written here 150 degree Celsius, that is T1. And he has asked determine the exit velocity of steam. So exit velocity of steam when the expansion process is ideal case, that is isentropic, and without isentropic. Okay, now so first we need to determine, or we need to find out the quality of steam or condition of steam at the inlet of the nozzle. That is very important point. So before going to solve the numerical, first you decide what type of steam is entering at the nozzle inlet, whether it is wet steam or dry steam or superheated steam. So to decide, first you note down the saturation temperature at 3 bar of pressure using steam table, that is table A1. Dear friends, we know that there are three types of steam tables are there. One is pressure basis values, and another one is temperature basis values, and the third one is superheated conditions, superheated steam. So first you need to refer one thermodynamic data handbook or steam table, that is A1. So here I have taken one thermodynamic data handbook, steam table. So what is the inlet pressure he has given? In our case it is 3 bar. So first go to 3 bar pressure. Here table A1, pressure basis. Here they have written thermodynamic properties of saturated water and dry saturated steam, pressure basis. Okay, so here is the value, pressure basis. So now we will go to pressure 3 bar. here 0.00602, the initial pressure starts from 0.00602. So go to 3 bar of pressure. So here is a 3 bar. So at 3 bar pressure, so what is the value of saturation temperature? 135.54 degrees Celsius. What does it mean is, if you are maintaining 3 bar of pressure in the boiler, and if the temperature of the steam is 135.54, then that will become dry steam. There is no percentage of water. Okay, but in the given condition, how much is the temperature is given? 150 degrees Celsius. Here is 150 degrees Celsius temperature is given, but from the steam table, how much you got? It is 135.54. So the given temperature is more than the saturation temperature. Okay, what does it mean is, if you maintain 3 bar of pressure in the boiler, and if your temperature is 135.54, it will become dry steam, but extra 15 degrees Celsius heat is they are supplied in the given problem. So the steam condition will become dry steam to superheated steam because of supply of extra 15 degrees Celsius heat. So the given condition is, it is not wet, it is not dry, it is superheated. For example, in the given problem, if the 150 degrees Celsius is not given, instead of 150, if they supplied 135.54 temperature, if it is given, then it will be dry steam. But the given temperature is more than the saturation temperature at 3 bar of pressure, so it is superheated steam. The same thing we have written here. The given temperature in the data is 150 degrees Celsius, which is more than saturation temperature. Saturation temperature at what pressure? That is 3 bar. So hence it is superheated condition. Now, so once you identify the type of steam at inlet to the nozzle, then take the values of enthalpy, entropy at inlet to the nozzle. So inlet to the nozzle, you will take it as first point, and outlet you will take it as second point, point number 2. So note down enthalpy, entropy, specific volume of steam using steam table, and A3 table, because A3 table is superheated steam table. The given temperature is more at the required pressure or desired pressure. So at 3 bar and 150 degrees Celsius temperature. So now I will go to superheated table. This is a superheated table, table A3. So what is the pressure which is given here is 3 bar pressure at inlet of the nozzle, and temperature is 150 degrees Celsius. So go to 3 bar pressure. This is 0.02 pressure. So observed pressure bar, and within the bracket they have given saturation temperature as well. So the given condition is 3 bar. Here is a 3 bar. Okay, at 3 bar, and what is the temperature at inlet to the nozzle? 150 degrees Celsius. So 150 degrees Celsius column, and 3 bar, the value of enthalpy, that is H, is 2760.4. And similarly you need a temperature, saturation temperature, that is 133.5, and also you note down the entropy, that is 7.0771. Understood? I will repeat it again. So at 3 bar pressure and 150 degrees Celsius temperature, here is the temperature is 150 degrees Celsius. So from 150 degrees Celsius temperature and 3 bar, note down all three values. Enthalpy, that is H, 2760.4, S, entropy 7.0771, and V stands for specific volume, that is 0.63374. So now I will take these three values, I will solve in the numericals. here I have taken 2760.4, 7.0771, and similarly specific volume. Here specific volume data is not required for solving the exit velocity, so if you write also no problem, but I have not taken it here. Now so now I will draw simultaneously HS diagram, enthalpy versus entropy diagram. So first you draw one dry saturated line, okay, and as we discuss in discussing the theory topics, the point which is if it is located on saturated line, then it will be dry steam, and if the point is below the dry saturated line, that is wet region. So these all are wet region, okay, and if the region of the steam or the point which is located above the dry saturated line, then it is superheated region. So this is all superheated region. Now in this numerical, the point number 1 is superheated region, so I have taken on the top of the dry saturated line, that is at 3 bar, point number 1, and we have taken H1 already. You have taken the value of H1. Now you draw one line vertical downward direction because it is isentropic process. So draw one line 1 to 2 downward direction. So take point number 2. So point number 2 is at 1 bar because in the given numerical he has given the expansion takes place up to 1 bar pressure. Okay, so point number 2 is 1 bar. Now we need to take enthalpy at point number 2, entropy at point number 2, and some similar properties at point number 2, that is at 1 bar. So timing, we have consider it as a conversion nozzle because specifically has not mentioned the numerical, so I have assumed it as conversion nozzle. Now to go to next step, step number 3, velocity at exit of the nozzle is with isentropic expansion, that is case 1. We will solve case 1 with isentropic expansion, and this is the formula which is used for calculating velocity of steam, that is C2 is equal to square root of 2000 into K. K is friction factor and drop in pressure or enthalpy difference plus C1 square. I have added plus because in the given numerical the value of velocity at inlet to the nozzle is given, so I have considered. If it is not given, you can neglect. So friction factor is not given, so I have neglect. Now at 1 bar pressure, that is P2, the value of enthalpy, entropy is listed here. So I will go to steam table chart, so table A1. Now point number 2 is not superheated, just see here, point number 2 is below the dry saturated line. If the point 2 is below the dry saturated line, then it is a wet steam. A wet steam is nothing, then enthalpy will be HF, HFG and SF entropy, and SFC is the entropy. Okay, it is not a superheated state, it is wet state, so normal pressure table will be referred. Okay, now I will go to 1 bar pressure, this is 2 bar, so go to 1 bar here. The second column represent the saturation temperature. Here second column is saturation temperature at 1 bar, 99.63. So at 1 bar 99.63 is the saturation temperature, and the value of HF will write down. The value of HF is 1.417.5. The value of HFG is 2257.9. Hg is 267.4, and here SF, SFG and SC. So these are the three values of entropy. Understood? So all these values we will list in the given data. Okay, this will be used for solving entropy or enthalpy, like that. So I will write here, on one side I have written HF2 HFG2. Point number 2 represents at pressure 2 or exit of the nozzle, because it is 1 bar pressure. So HF2 HFG2 SF2 SFG2 is done. So now to calculate H1 already have calculated, but H2 we don't know. So to calculate H2 is wet steam. Understood? It is below the dry saturated line. So to calculate H2, what is the formula? H2 is equal to HF2 plus X2 into HFG2. HF2 and HFG2 we have taken from the steam table, but we don't know the value of quality of steam at point number 2, that is X2, dryness fraction. We don't know. So to calculate the dryness fraction, we assume that it is isentropic expansion process. Isentropic expansion process. So during isentropic expansion process, entropy will remains constant, that is S1 is equal to S2. So if you apply this condition, S1 is equal to S2, S1 already are taken from the superheated steam, that is at point number 1. S2 is equal to entropy at point 2, because it is wet steam. Whatever the formula you applied for enthalpy, same formula will be applied for entropy. SF2 X2 SFG2. And yes, this is the formula used for calculating enthalpy of wet steam. Okay, if you can use the same formula for calculating enthalpy of dry steam, but X will be equal to 1, because you are using the word dry. Dry is nothing but X is equal to 1, that is 100% steam, no water particles. So here all the values are known values except X2 value. So use mathematical equations and calculate X2 0.95. Now substitute the value of X2 in equation number 2, calculate H2, and that H2 value will be 2562.5. So now equation number 1, we know H1, we know the value of H2, we know the value of C1 square, which is given in the numerical, and K is neglected, we will take it as 1 because not given in the data. So square root of 2000 H1 value minus H2 value, and you will calculate C2 is equal to 635 meter per second. This is the velocity of steam which is coming outside the nozzle using case 1, assuming isentropic expansion. Now same for the same condition, for the same given data, we will assume that isentropic expansion is not there, it is irreversible or non-isentropic process. So when it is non-isentropic process, efficiency of the nozzle is not 100%. So how much efficiency has given? 95% is given in the problem. How much is given? He has given 95% efficiency here. So considering 95% efficiency, again we will calculate the exit velocity of the nozzle. So obviously the exit velocity of the nozzle with 95% efficiency will be less, because there is a 5% error. The case 1, expansion is isentropic in nozzle, this is 100% efficiency of the nozzle. So we got some velocity 635. By considering some friction or some loss of 5% energy, the velocity will be less. So now we will calculate the velocity at exit of the nozzle, then we will compare answer with the previous one. The answer for the second case should be less than 635. Now exit velocity of steam with nozzle efficiency 95%, that 95% will be written as 0.95. So see, to same formula we will write as it is. So only the thing is, instead of neglecting the efficiency of the nozzle in the previous case, now we will consider efficiency of the nozzle. Obviously if K is given, you consider K, but here K is not given, I have already neglected it. So 2000 as it is, H1 value will be same, he has not changed any values. H2's condition of at exit of the steam is same, and efficiency of the nozzle is 0.95. So C1 is net velocity of the steam. So you simplify this equation and square root of the answer, you will get 619.76. What is the previous answer? How much is the velocity? The previous one was 635, assuming 100% nozzle efficiency, 635. Now, and the nozzle efficiency is only 95%. There is a 5% error, there is a decrease in velocity of the nozzle, so you got 619.76. So this is one method for solving numericals on steam nozzles. The other method is using Mollier chart. So this method is very simple, but you have to be friendly user with Mollier chart without using steam tables. Here we will not use the steam tables, directly we will use Mollier chart, that is entropy versus enthalpy diagram, HS diagram. Now, so first step number 1, using the Mollier chart, first locate point number 1 on HS diagram. Point number 1 is what? That is, what is the condition he has given at point number 1? That is inlet of the nozzle, 3 bar pressure, 150 degrees Celsius temperature. So go to Mollier chart, at 3 bar line and 150 degrees Celsius temperature line, the intersection of 3 bar pressure line and 150 degrees Celsius temperature line, the intersection point will give point number 1. Okay, I have written here, locate point 1 on HS diagram. Okay, point 1 is the intersection of pressure, that is line 3 bar and 150 degrees Celsius temperature line. Once you locate the point number 1, note down H1 value at point number 1 and similarly S, that is entropy value at point number 1. Now you will go to Mollier chart, and this is the Mollier chart diagram. Okay, so this is Mollier diagram in SI units. The horizontal line is specific entropy and vertical lines will be specific enthalpy. And dear friends, on both the sides the values are same. Here enthalpy lines, here is also enthalpy line. On the top of the chart, again specific entropy. The top values and the bottom values are same. Okay, the reason is, if you are taking the values at this point, not you can take the entropy here instead of stretching the line vertically on the upper side. If you are taking the value of enthalpy at this point, no need to stretch the point up to here. You can go back to on the right hand side, you can measure the enthalpy. That is the reason on both the sides they have given the enthalpy and entropy values. Now I will locate point number 1 at 3 bar pressure and 150 degrees Celsius temperature. And dear students, here 50 degrees Celsius, all of you see here 50 degrees Celsius, this line is 50 degree, this is 100 degree, here 100, 150 degree. Okay, this line 150 degree, 200 degree, here is also written 200 degree, at the same time 200 degree also, here is also they have written. This is 250 degree, and similarly 300, 300, 350, 400, like that. Okay, now the pressure lines, here is the pressure lines, this is the pressure line 1.0 bar, this curved line 1.0 bar, this is 1.5 bar, this is 2 bar, and this is 2.5 bar, and this is 3 bar, and similarly 4, 5, 6, 7, 40, 100 up to 1000 bar pressure values is given in the Mollier chart. For our case, the inlet pressure is 3 bar. Now you take this curve, okay, and at the same time 150 degrees Celsius temperature. Now I will take 3 bar line, this is 3 bar, and here is 150 degree, this is 450, 400, this is 250, 200, 150 degrees Celsius. Now locate a point with, this is 150 degrees Celsius line. This is 150 is here. At the same time they are working here 150 degree. This is a 150 degree line, and 3 bar. This is 1 bar, this is 2 bar, and this is 3 bar. Cross check. This is 1 bar, this is 1.5 bar, 2 bar, and this is 3 bar. This is the 3 bar line. And dear students, I am locating the point. This is 3 bar line. Observe carefully. And here it is 1 bar line. The numericals on using Mollier chart is easy actually. Instead of solving using steam tables, it is very much easy using Mollier chart. So 150, and here is 3 bar. This is 2.5. There is 3 bar. So intersection of these two is here at this point. So this point I will take it as point number 1. Understood? So intersection of 3 bar pressure line and 150 degrees Celsius temperature line is, this is point number 1. So once you locate point number 1, take enthalpy. Either you using scale, you take an horizontal scale and take the value of enthalpy on the left hand side, or else using on the right hand side you take the enthalpies. For example, we will stretch this line here. This is point here. So what will be exactly the value of enthalpy? This is 2700. Here it is 2700, and between 2700 and 2800, how many lines are there? 1, 2, 3, 4, 5. So each digit gives 20 enthalpies. So 2720 is the first digit, 2740, and this is 2760. So on an average 2760 is the enthalpy at point number 1, that is at 3 bar pressure line and 150 degrees Celsius temperature line. So that is 2760. So here how much value have taken? 2760. Understood? So at the same point you note down entropy. Or it is not required here, because in the formula for calculating C2 you need only H1 and H2, not required S1 and S2 here. So not necessary to take the value of entropy at point number 1. Now, so once you locate point number 1, at the same time here also I have shown how to locate point number 1. That is what just before I have shown you in the Mollier chart. Now here 3 bar line you have taken, 150 degrees Celsius line you have taken, the intersection of these two curves, you have taken it as point number 1, and you have taken the enthalpy between 2800 and 2700, you got 2760. Okay, it is not an average. Okay, point number 1 you have taken the enthalpy. Now step number 2 is, once you locate point number 1, draw vertical downward line, because it is isentropic process. Expansion of steam in the nozzle is isentropic. So from point number 1 you draw a downward line up to, that is exit pressure of the nozzle is how much? 1 bar. So for up to here you have to draw one line. So go to Mollier chart. Here is the Mollier chart. The point number 1 was here on an average. The point number 1 is here, you have shown. So from point number 1 you draw one vertical downward line. So point 1 you draw one vertical downward line up to 1 bar pressure. Where is 1 bar pressure? This is 0.2, 0.3, 0.4, 0.5, 0.75. This is 1 bar. So from here to here, the small length. Now I will stop here. This is 1. Understood? So point number 2 will be here, that is just below the dry saturated line. Here it is a dry saturated line, the thick line, what it indicates, it is a dry saturated line. So point number 2 is here. So at this point number 2, here is the point number 2. So this point number 2 you take again enthalpy, that is H2. From here to here you stretch one line. H2 will be on an average. So this is 2500, and each digits, the distance between the two lines is 20. Each digit is 20 value. So 2500, 2 plus 20, 2520, 2540, 2560, 2580 and 2600. Now the values of H2 at point number 2, which is located here, which give on an average approximately 20, 40 and 60, 2560. So we'll go to steam nozzles. So you have taken the value 2570. There is a slight variation in enthalpy values using steam table and Mollier chart, because it is purely based on visualization. Okay, the person who has some good eyesight will measure the correct values. Okay, but on an average no problem. So 2570 is the value of enthalpy at point number 2. So using equation C2, so 2000 square root H1 minus H2 plus C1 square. This is the formula for calculating velocity at exit of the nozzle. Dear students, be careful. Many of the students will do the mistake here. They will write the another formula what you have given in the listed, 44.72 square root of H1 minus H2. So when you are considering the value of C1 square, it will not become 44.72. We cannot take 2000 outside the square root. If you neglected the C1 square, then this value will become 0 plus 0. Then you can take 2000 outside. But when you are considering the value of C1 square, that is initial velocity, we cannot take 2000 outside, so we cannot use this formula. So that is the reason I have written here and I have strike out. We cannot use this formula. Understood? So 2000 will be within the square root. Substitute the value of h1, that is 2760, and substitute the value of h2, 2570. Understood? Plus 90 square is the initial velocity. So you simplify this equation, it will become 630 meter per second. But in the previous, using steam table method, the value of C1, C2 using steam table, we got 635. The 5 meter per second is an error because Mollier chart is a little bit error, but and it is purely based on visualization, how much care you take to locate the point. If you do some small mistakes in locating point number 1 and point number 2, there will be slight variation in the enthalpies. And with case 2 is 95% efficiency. So same formula with 95% efficiency, that is nozzle efficiency, I will multiply here. So square root of 2000 h1 minus h2, efficiency of the nozzle, plus c1 square. So values will be remain same. So substitute the values of h1 and h2, put the value 90 square and nozzle efficiency, calculate velocity at the nozzle, that is we will get 607 meter per second. So this is the velocity at exit of the nozzle. So, and dear student, this is how the numericals on steam nozzles will be solved using Mollier chart. Okay, so we will glance for 1 minute. So there are two methods to solve numericals on steam nozzles. One is using steam tables, another one using Mollier chart. So using steam tables, this is the method 1. First you identify the quality of or the condition of steam at inlet to the nozzle, whether it is wet steam, dry steam or superheated. How will you identify? So based on the given pressure. At the given pressure, you note down the saturation temperature. At the given pressure in the steam table, note down the saturation temperature. If the temperature which is given in the numerical, if it is more than what it is given in the steam table, then assume that it is superheated. If it is equal, both the temperature values are equal, assume it is dry steam. If the given temperature, the given data temperature, if it is less than what saturation temperature you will take from the steam table book, then it is wet steam. Understood? So once you take the value of H1, note down from steam table books, locate the point H1. Okay, so calculate H2. H2 is equal to enthalpy of wet steam using this formula. So once you calculate H2, substitute here, calculate velocity in the equation. So this is for the first case, case number 1, method 1, but case 1, expansion is isentropic. For the using method only, case 2, nozzle efficiency is 95%. So nozzle efficiency is 95%. I have considered. Only you have to multiply with the efficiency of the nozzle within the square root of 2000. Okay. So with this considering 95% efficiency, we got C2 is equal to 619. So second method is using Mollier chart. In question paper, specifically he will ask you have to use Mollier chart or use steam table only. So if you ask Mollier chart, if and you solved using steam table, you lose the marks. Understood? Specifically he will mention the solve this numerical using Mollier chart only, then you have to go for Mollier chart, no chance of using steam table. And if he has not mentioned particularly not Mollier chart or steam table, you can choose which one is best, which one is easy for you people. And you, but compared to these two methods, Mollier chart is easy, but you have to be careful with locating the points. Okay, there will be some error. So at point number 1, that is 3 bar 150 degrees Celsius. So 3 bar pressure line, that is curved line, and 150 degree Celsius horizontal temperature line. It is not purely horizontal, it is also curved but not like pressure lines. So intersection of these two line is point number 1, that is inlet to the nozzle. Once you locate point number 1, take the enthalpies H1 in the Mollier chart. So after taking the value of H1, draw one vertical downward line up to where you will stop. The extension of this line is up to 1 bar pressure, because the exit pressure of the nozzle is given as 1 bar. So up to 1 bar, locate the point, take the H2 value. So H1 and H2 is known value now. So substitute the value of H1 and H2 in the equation of exit velocity. Substitute all the given values, calculate C2, and similarly for the second case also. So this is how the numericals will be solved. So in next lecture we will solve one more Visvesvaraya Technical University question papers problems. Okay, thank you so much for watching this video lecture. Bye bye, take care.